Right, so we were talking about this reaction. Now, I'm going to book a whole bunch of demos to show you guys. Rates is one of the fun sections where we can do some nice demos, so I'll book them for later on in the week. Mr. Steigen, please get your mask sorted. We won't just be talking about things theoretically, we'll also do a prac on it, so you'll get a chance to see some of the stuff a bit more practically. Trey, you got a question? Yeah, and so, all right, Sebastian, you're making life difficult for me and your mask off, so we'll call that strike one. So guys, the characteristics of different reactions and different chemicals, all the ones we deal with in class and the ones that are in the notes, we expect you to remember. So all of these reactions, if I mention a chemical and what color it is and all that kind of stuff, we expect you to remember it. Okay? If it's in the notes, if we've done it in class, it could come up. All right. So we were speaking about this one, and we said different ways that you can measure the rate of reaction. Here's two examples in front of you. If you were measuring the volume of CO2 for this reaction as the reaction was proceeding, and you drew a graph of the volume of CO2, what do you think the graph would look like? Would it be A, B, C, or D? Don't shout out, think about it for yourself. You're measuring the volume of CO2 using a system perhaps like this, where the CO2 is collected in a flask, and you can measure you can record how much CO2 is given off every minute, or every 10 seconds or something. What would you expect the graph to look like? A, B, C, or D? Okay, just think about it. Make up your mind on the volume. Is the volume going to increase? Is it going to increase uniformly? Is it going to increase fast and then slow? Is it going to get to a point where it stays constant? And then think about this one. What happens if you decided to do it using mass? Now, to do mass, you would use a different setup. You would just take this stopper with the gas jar, gas syringe out, and you'd have an open container, and you could throw the calcium carbonate into the reaction vessel, but you could do the reaction on a mass balance, electronic balance, so that you can read the mass value as the reaction is taking place. And if CO2 is given off, then the mass of the container should go down. Now, how would it go down? Would it be like A, like B, like C, or like D? Think about it. I know I haven't taught you this, just think about it. What's changing as the reaction proceeds? CO3 is reacting with HCl. How would it change with time? Okay, let's see some guesses. For volume, hands up for A. Hands up for B. Hands up for C. Hands up for D. So you all think it's B. And mass decrease. Hands up for A. Hands up for B. C. Obviously it's not a decrease. And D. Okay. B and A. So you're all right. It happens fast initially. Why does it happen fast initially? There's lots of collisions because there's high concentrations. But as some of the reactants react and more products are formed, the concentrations drop, so there's less collisions. So the rate of reaction decreases. Now these graphs, the rate of reaction would be the gradient of the graph. How fast the concentration is changing per time. These graphs are supposed to be, this is volume over time, mass over time. And the rate of change would be the gradient of the graph. So you're all happy with that? Right. So when you get rate graphs, if you take a reactant concentration, obviously it's going to decrease, but it'll decrease fast initially, like we've just said, and then it'll decrease slower as the concentration drops, and then eventually, when all the reactants are used up, the reaction rate graph will be horizontal straight line because the reaction will have stopped. Happy? That's reactants concentrations. I don't know why I did that graph twice, but anyway. Yes, for reactants. It might not be exactly like that. It might drop slower or slightly faster, but the general shape will be correct. So there we got the same thing. If you did so there's a reactant rate graph, just like I showed you there. Here's a product graph, and you can see with the product, obviously it's just going to be kind of like the inverse. It's going to increase fast, then it's going to increase slower. As the reactant concentration decreases and the rate of the reaction slows down, the products will be formed slower. And then when all the reactants are used up, the reaction will have stopped. And so the concentration of the product will remain constant. Happy? It's chemistry. Chemistry. So, we need to fill in a couple of things here. The reaction rate can be, there's the definition again, the rate at which reactants are used up or products are formed. In a general reaction, A plus B going to form AB. The rate will be inversely proportional to the time taken for the reaction. Yeah, that's inversely proportional. Well, they're directly proportional, but if you've got 1 over time, then it's inversely proportional. So that's inversely proportional to time. Obviously, the reaction takes a long time, then it's got a high rate. If the reaction's got a low rate, it'll take a short time. And so we often use rate 1 over time to represent the rate. The rate would be equal to one of the concentrations, to how much they're changing over time. And then if we gave you a graph of concentration, we could ask you to find the rate, and you just have to find the gradient of the graph at that point.
Reaction rate is just the rate. The reaction rate.
It's reaction rate, yeah. Now, the thing is, the rate is changing the whole time because it's fast and then it's slower and slower and slower. So if we ask you to find the rate, we'd have to ask you to find the rate at a particular point. Yeah? Normally what they do is they talk about the initial rate, because can you see the initial rate of the reaction? The initial part of the graph is almost a straight line, right? So what we do is if we talk about reaction rates, we normally talk about the initial rate, and that means just the rate just after 0 seconds, the first little bit of the graph, which almost looks like a straight line before the rate begins to drop off. Okay. So normally if we do ask you to do that, you'll just use a slope, and you'll do the slope right near the beginning of the graph. Fine. When you see square brackets like that, you need to know that what we're talking about is concentration of that substance, and usually in moles per decimeter cubed. I don't know why that decimeter cubed symbol went to the bottom. It should be up. Moles per decimeter cubed. All right. So. Yes, I know. I'm sorry. I should. I should not have used that. But it's not a lot. Don't worry about it. You can see it better on your own screen. And when it's printed out on the thing, it's fine to see. So it's not the end of the world. Agree? Good. Right. So. Chemical reactions. What has to happen for chemical reactions? If A is going to react with B, right, they have to collide with enough energy to break bonds. And if they do that, and they collide with enough energy, then old bonds can break and new bonds can form. Right? So we call it, they must undergo an effective collision or a successful collision. And for that collision to be effective, they've got to have enough energy, and they sometimes have to have the right orientation. Sorry, what's the matter? Yeah, look, I can change the. I'll change it. What? Oh, flip. Made it worse. Okay. Good. So the rate is down to the number of effective collisions per second. Now I know you might be looking at this thinking, oh, flip, so this is so easy, and it's, you know, how can we get this? It's going to be strike one. So one of the places where people often lose marks here is we ask them to explain something, explain the effect of temperature, or explain this, or explain that. And you have to go down to collisions. But you have to talk about the rate of collisions, right? And you either have to say the rate of collisions, or you've got to say the number of effective collisions per second. You can't just say more effective collisions, or not even just more collisions. It has to be more effective collisions per second. The number of times I have guys fighting with me in a test because they've lost a mark on an explanation, and they lose the mark because they don't say either rate of collisions, or rate of effective collisions, or they don't say number of effective collisions per second, right? So this per second bit is hugely important. You can't forget it in your explanations. Now, what kind of things do we have to understand? Well, what are the factors that affect rate? There's a whole bunch of them. We've spoken about it before. I think it's self-explanatory. I've got yellow writing again. One of the factors that affect reaction rate is going to have to be concentration. If you've got more reactant particles per centimeter cubed, there's going to be more collisions. And if there's more collisions, then there's more chance of a effective collision. Effective collision is a collision that we explained 2 slides back. Correct energy and correct orientation, right? So those are 2 factors. If you increase the concentration, obviously you're going to increase the number of particles per second and the greater chance of collisions. And if there's more collisions, there's more chance of effective collisions. Because a certain percentage of your collisions will be effective, depending on the temperature and the orientation. So if there's more collisions, there's probably going to be more effective ones. Now, for liquids, that will be governed by concentration, but for gases, that will be governed by pressure. Right? Because if you increase the pressure of a gas, you get more particles in a smaller space. Happy? So, here I'm trying to show 2 factors. This is, a 1 molar potassium permanganate solution. You can see it's more dilute. A 2 molar potassium permanganate solution, obviously more dilute, more concentrated. And for a gas, if you squash it, the particles are closer together, more chance of collision. There's more particles per volume. So increasing both of those things will increase reaction rates. Concentrations for liquids, pressure for gases. What about solids? Can you increase the concentration of a solid? Not really. Most solids have got a fixed density, right? Now, a more dense solid might react better or faster, but you can't change the density of a solid. Yeah. Temperature is always going to work. Let me go here. Temperature is always going to work. Why is temperature always going to work? What is increasing the temperature do? Move quicker. So if there's more collisions per unit time, then there's probably going to be more effective collisions. But temperature has a double effect. Not only do you have more collisions per unit time, but the collisions that you do have will be more effective because they're going to be faster. Sorry, not happening faster. They're going to have more energy because the particles are moving faster. So you are changing 2 things when you increase the temperature. You're changing the number of collisions per second, and you're increasing the energy of the collisions. So a small increase in temperature has a massive increase in reaction rate. They say, and I don't know where this comes from, but apparently this is the case, a 10-degree change in temperature will almost double the reaction rate of most reactions. Now, 10 degrees is not necessarily doubling the temperature. I suppose, if it's at 25 degrees C, which is room temperature in South Africa, 10-degree increase is only a third increase, 30% increase in the temperature by about 30%, and that doubles the reaction rate. So increasing the temperature has a much bigger effect on reaction rate, usually, than almost anything else.
So if you doubling temperature, then you have to do it from
That's correct. But a 10-degree increase from at 25 degrees wouldn't be doubling.
So, how like today, surely people are more irritable today, like the particles in the body are moving faster, and they're like more restless, and
well, I wouldn't know the exact mechanics of it, but I certainly am more irritable on a hot day. How it actually works, I'm not sure. You just get more tired. I think you get, perhaps reactions are happening faster in your body, and things that would have taken longer to use up energy, you're now using up the energy faster. Although on a cold day, I don't know. They do say that cold actually stimulates you. So they reckon it's easier to study when you're cold. But it's also easier to sleep when you're cold. You need to sleep when you're cold, yeah. All right, so again, why does it work? Because you've got more energetic collisions and you've got more collisions per unit time, a higher rate of collisions. The average kinetic energy of the collisions increases and the particles move faster. That picture there is supposed to be a cold surface, a warm surface, and a hot surface, and you can see the things have got hotter. Now, so if it doesn't work for solids, if volume, we've got volume and pressure, volume for gases, concentration for liquids and pressure for gases, what happens with solids? Well, think about this. If you had a certain size of something, so you've got a piece, you've got a chunk of something. I'm just considering area now because I'm not going to do it in 3 dimensions, but it's the same concept. Here we've got a chunk of something, and here we've got another chunk of the same thing, but here we've cut this chunk into 4 pieces. And both of them the same size. The dimensions from here to there are 2a. And dimensions here are 2a. Now, solids, how do they react? You can't react on the inside of the solid. You have to react with the surface. So surely if you've got a bigger surface area, you're going to have a fast reaction. Well, how much surface area have you got here? If you're just going, now what I do is I work out the circumference. So imagine it's a 2-dimensional thing, it's going to react just from its edge. How big is the circumference? The circumference here is 2a times 2a times 2a times 2a. So it's 4 times 2a. Total perimeter, 8a. Right? Yeah. Yes. It has to rust on the surface first. So if you just think about the perimeter here, you've got a total perimeter of 8a. If you cut that into 4 pieces, what happens to your perimeter? You've now got A, and A there, and here you've got A, and A again. So you've got 4A, 4A, 4A. You've got a total perimeter of 16A. By cutting it into small pieces, you get a bigger perimeter. I used to think, South Africa's got a massive coastline, much bigger than, like a small country like the UK. The UK's coastline is actually much bigger than South Africa because it's got so many little islands. It's much bigger. So with a solid, if you want a solid to react faster, you must break it into smaller pieces. Now we know that anyway, don't we? Every time you have a braai, what do? To start the fire. Get big sticks, chop them into smaller ones. Because they react from the surface area. There's a whole bunch of examples of this. In the old days, it used to be a lot more, people working in coal mines. What was the issue, the problem in coal mines? Well, one of the problems. Apart from lots of earth falling on your head. Not breathing in coal. Why did they have canary? No, not canaries. So one of the problems with coal is this. In a coal mine, you get lots of coal dust. And coal dust mixed with air is almost explosive. It'll explode. You want to try and light a big lump of coal, it's not easy. But grind it into a fine powder, it'll flash. So coal dust with air, you get a spark, you can have an explosion. You can cause an explosion using, if you know what you're doing, using custard powder. Powders burn like anything. Nick is strike 2, I'm afraid.
So you're using like powder for the reflow.
Yeah. So that's this effect. It's the surface area effect. If you make the surface area bigger by making the pieces smaller, the reaction rate increases. So And this only works with solids. Okay? Factors affecting reaction rate. That's only for solids. And if you increase the surface area, the solid will react faster because solids react from the surfaces. So make sure you've got that. Okay, so we're cracking through the theory. We'll get to some examples in a minute. Now, here's one example that, and this is one of the ones which it's actually been in past paper questions. And guys, when you read the details of it, it kind of throws them, but it doesn't need to. So look at these two reactions. Okay, now you've got to look at the detail here. Sebastian, strike one. I must keep note of these strikes because I'm going to lose count. So have a look at these two reactions here. This first one, you got the reaction on the left here is potassium permanganate, and it's reacting with iron chloride and with HCl. And what's actually happening to the potassium permanganate? It's becoming MnCl2. Now, if you remember, anybody know anything about potassium permanganate? Remember I said you need to start remembering some details of chemicals. Strong what? No. Oxidizing agent. Massively strong oxidizing agent. What color is it? Dark purple. Now, if I was you, I'd be scribbling that underneath there. Okay? Yeah. Dark purple. The MnCl2, the manganese 2 plus ions, are very pale pink. So pale pink that they actually look colorless. So this solution would go from dark purple to colorless like that. Now that's the kind of thing you need to remember because they'll mention it in an exam question, and if you don't remember it or know what they're talking about, it could throw you. The iron, what's the iron doing? Well, this is iron 2, FeCl2 is iron 2. This here is iron 3, FeCl3. So the iron, what's happening to the iron? Going from 2 to 3. What do we call that? Oxidation. It's being oxidized by the oxidizing agent, which is permanganate ion. Okay, Nick, you're bugging me at the moment. So, permanganate's been oxidized to permanganate ions by the iron chloride. Okay, look at this next reaction. You got potassium permanganate. Excuse me. And it's also reacting with a whole bunch of stuff. There's some acid there as well. Reacting with this stuff, which is oxalic acid, it turns out. You need to know oxalic acid's formula because we use it in the acid-base titrations also. So that shouldn't be news to you. Oxalic acid. Now, the permanganate again is becoming Mn2 plus ions. I know that's Mn2 plus because I know that SO4 is 2 minus. So it's the same reaction as far as the permanganate is concerned. All right? So why are we giving you these two? Well, this first one happens really fast, and the second one happens slow. And you expected to know why. Or, yeah, you expected to know why. And the reason why the second one happens fast is that this oxalic acid molecule is it's a big molecule. You can see it's H2C2O4. There's a lot of covalent bonds there. And to break that down needs lots of energy, and it slows the reaction. It's a complex molecule. Whereas here, in the first reaction, the iron chloride is just an ionic compound. It's aqueous. When you put it in water, it just breaks up into its ions. So the ions are free to react. So this one is fast because you're reacting with a simple ionic compound. This one is slow because you're reacting with a complex covalent molecule. Jason.
So was there a reason why you mentioned the reaction numbers?
Yeah, well, we just expect you to know that manganese 2 plus is, because they'll talk about the color of this reaction. It goes from purple to clear.
The second one.
It also goes from purple to clear because the manganese is causing the color. The oxalic acid is colorless.
The manganese in KMO4, the Mn is 7 plus.
No, that in MnSO4. MnSO4.
Yeah.
The manganese is 2 plus, yeah, the same as it is here.
KMO4 minus.
KMnO4 minus, it's 7 plus. That's why it's such a strong oxidizing agent.
I don't know what that has to do.
Well, that's what's actually happening. It is oxidizing because it's in +7 state. It's very high oxidation state. It can take electrons away from other things. So it's taking electrons away from this oxalic acid. That's why it's reacting. It's the same redox reaction, it's just, yes, exactly. So it's the same redox reaction in terms of the magnesium, but it's faster in the one, slower in the other one, and you need to know the reason why. All right? And the reason is in the bottom here in red. The difference in rates observed here is because simple ions can react faster than complex ones. Now the problem that you've got is this. They can give you, here I've just shown you the structure of the two compounds so that you can see why it's more complicated. Obviously the oxalic acid on the right here is more complex. The simple ionic compound on the left, just going to break up into its ions, and they're all loose and they can react instantaneously. It doesn't. Oxalic acid would display hydrogen bonding, but it's not involved in the process at all. Yeah. Yes. It's about, yes, it's about how many bonds has to be broken for this thing to react. Well, no. In iron chloride solid, the bonds are very strong. But it's in an aqueous solution, so the ions are just free to. Yeah? Yes. Are you talking about the iron chloride? In general. If there's less bonds, it would be quicker, yes. Less bonds to break. Okay. Now, we need to talk about Maxwell Boltzmann. Let me just see how we're doing for time. 2 minutes. Okay, so we won't start talking about Maxwell Boltzmann now. We'll go into that next lesson.